Welcome everyone to today's webinar. So today we are talking about thermal management of batteries using COMSOL and Simulink. So it's a joint topic between the two software solutions, so we will cover them. Today we will talk a little bit about COMSOL Multiphysics. So what is it? What kind of software solutions can it offer? What kind of other solutions can you achieve with that one? A few words and slides about thermal management. What is it? What can you think about this? Why is it that important today? Some features from the heat transfer modules. What's the capabilities of that? How you can access, what solutions can you expect from it? And a few words about the multiphysics simulation of thermal management with a live demonstration. So we will switch from COMSOL and we will see a recorded solution running a full Simulink model with an embedded high fidelity model of COMSOL Multiphysics, a high fidelity finite element model here. And at the end, we have a Q&A session so we can answer your questions. Let's talk a little bit about COMSOL Multiphysics before we jump into our demo today. To realize the full benefits of simulations, such as shorter product development times, greater insights, more innovative designs, ability to reject flawed concepts early, and so on, and other things. So these models need to account for all the physics that affect the outputs they are trying to predict for. In other words, so if you ignore some important physics, your model is not going to be high fidelity. And many, probably most systems that engineers analyze involve multiple physics. For instance, so if you want to predict how hot a laptop gets, you may need to consider chemical reactions in the battery, Joule heating in electrical components, airflow affecting cooling, and so on, and other physical effects here. So it's not just a heat transfer equation you need to solve to get accurate predictions, but more. And that's the whole philosophy of COMSOL Multiphysics. So it enables the modeler, you, to combine arbitrary physics together, no matter how intricately they may be coupled, and to build powerful, flexible, accurate models. So the software even allows you to add your own equations, should it be necessary. And the major innovation of COMSOL Multiphysics is the application builder. So the application builder is the right tool that lets you turn your sophisticated model, any model, into an easy-to-use app that your colleagues and customers who are not into modeling can use. And this enables them to contribute to the analysis process. This is the current product suite that we are looking at currently. So we have 4 different physics areas grouped into electromagnetics, structural acoustics, fluid and heat, and chemical reactions. So this covers our major physics phenomena, and there are so-called multi-purpose modules like the optimization or the particle tracing module. So if you are going to optimize your design to dissipate as much heat as possible or increase output power as much as possible as the design limits, you can combine this optimization module with any other physics. So today we are going to deal mostly with the functions from the battery design module. And also there are so-called interfacing products like the live links. One of these is for the live link for Simulink. So if you happen to investigate a PID controller of a battery management system, you can use Simulink for that purpose and with other tools. And you can include a high fidelity finite element model of the battery pack itself. So in this sense, you can create a so-called cost simulation. And that's what we are going to discover today. And one of the new features that came out just a few months ago is the model manager. So, and from my experience, what I'm hearing from our customers, that they are looking for a place and a tool to manage different model versions, revisions, parameter sets, and setups. So this model manager is a tool for simulation data management. And this model manager makes it possible for users to collaborate and centrally organize models. And this model manager gives you version control to systematically track changes and updates to models, is also integrated with and directly accessible from the user interface. And you can use a local database or connect to a remote server database. That's also an option here. There are options for efficiently storing models and apps, which only relevant data of drafts and revisions, as well as auxiliary data such as CAD, mesh, and experimental data. You can also configure COMSOL Multiphysics to always only store in the database the information needed to reproduce the model without mesh and solution. And this model manager also includes advanced search functionality that allows you to find models and apps in a database by using a user-defined tags or searching for certain features or parameters. For example, which interface are built with the solid mechanics interface, or which models have a parameter named capital L and which have the parameter value greater than 0.5. So you can control access to models with user groups and permissions. So this is the model manager in short. And on the deployment side, there are also the COMSOL compiler. So this allows you to create standalone applications from any of your finite element model. So in this sense, you can share it with customers, other persons inside your organization to show the simulation capabilities and the solutions that you have achieved. Another way to share ideas with others, maybe with others outside your organization, is a COMSOL server. In this sense, you can host your applications in a COMSOL server, which is a file server, and anyone who has access to that server with using only a web browser, he or she can easily access your simulation applications. Okay, and let's turn our attention into the thermal management side that we want to discover today. So this thermal management covers a lot of places. It happens in a very wide range of areas. So in this little figure, you can see an electric component with capacitors, heat sinks, fans, ventilations that mainly cover all the aspects of heat transfer. And there are different versions of this: convection, conduction, maybe radiation. So you can have solutions for all of these. You can investigate whether a passive radiator is enough for your design, or maybe you need some active cooling in your equipment. That's also possible. You can search for the steady state solution, or you can search for the time-dependent simulation as well. The heat transfer module has the features like I mentioned earlier: conduction, convection, radiation. If you want to couple to other physics like electromagnetic Joule heating, you may need additional toolbox modules here. And what we cover is the battery design module, specifically for creating and designing batteries, examining properties of it, thermal management side, and other fluid related sides. The coupling can be one or two-way coupling based on your needs, and you can have several studies types. Okay, and also to couple to other than heat transfer, you could include, let's say, a Joule heating example here. So if you have some electromagnetic source that works as a heat source, then this can be coupled into your model. The properties can be temperature dependent, and you can use these variables during your simulation. Okay, and from our side, so we will use a so-called lambda battery, which is a very nice interaction here. So that's one sort of interface that we are going to investigate. So it's quite fast and accurate model to model batteries on their own situations and setups, and quite easy to set up. And we can create multiple arrays of these batteries to create battery packs, and we can quickly investigate the effect, the thermal distribution, the temperature distribution of these packs, and we can evaluate those properties quite easily. And it's quite easy to solve. And going a little bit further on that, so we have this live link for Simulink here. So with this, it makes it possible to perform simulations of COMSOL models with Simulink. So this makes it possible to integrate multiphysics modeling with control design and simulation performed with Simulink and Simulink blocks. Both static and time-dependent models are supported, and the battery pack discharge control model with thermal analysis. And this example will compute the temperature distribution in the battery pack during a 4C discharge. So the problem is that we want to ensure a constant output power and prevent extreme battery usage condition. So the multiphysics model is coupled to a control diagram that's made in Simulink. Okay, another solution here. So there are some built-in models. That's one also available here, and we will send you the link to that in the follow-up email. And the workflow is as follows. So you set up the co-simulation parameters, the inputs and the outputs inside the dedicated feature inside COMSOL Multiphysics. Then you start Simulink and you drop this COMSOL co-simulation block into your model. You set up the parameters, the controllers, whatever you need for your design. And then you can run the simulation inside Simulink, and then you can post-process the results there also. So that's the current workflow here. So let's go into our COMSOL model and let's take a look how it is set up here. So if we go into our model, here we can see that we have some geometry parameters. Anything and everything can be a parameter inside COMSOL Multiphysics. So you can group the parameters into different sections. So you can have a separate parameter list for the battery parameters, like the cell capacity, the load in amperes, different features and constants that are relevant to our model. And then here we have a dedicated node for co-simulation for Simulink. And as we see that there is one input here, which is the applied current. So that will be one and single input for our model here. And then we have outputs like the cell voltage, the temperature of the cell, and the charge of the cells. So these are the three outputs that will be used for the functional mockup unit that we will create from this model. From the physics side, we have a heat transfer in fluids, which is defined here. So we have these solid blocks with all the relevant properties. And of course, because these are little cylindrical batteries, the conductivity, the thermal conductivity is uneven. So in the different directions, it have different values, since these are little foils wrapped around this axial direction. So in the radial and the two other tangential and the other spherical direction, the conductivity is not the same. So you can set up this way. And the same goes for the other two battery packs, and the little connections are defined with copper. So this is the heat transfer part. And for the battery part, so we use this so-called lumped battery interface. So here in the equation node, you can see this is the equation defining our behavior of the battery. And this is quite lightweight, it's easy to compute, so it can be run much faster than a full high fidelity battery model with separate properties. So we have one physics interface for each of these batteries, as you can see here. And from the multiphysics node, so here we can define the coupling between the physics, so between the battery interface and the heat transfer in fluids interface. So in this sense, it's quite easy to define a two-way coupling between the two physics. And that's from the COMSOL side. And then if we save this as a functional mockup unit and go into the Simulink side, we can run the simulation inside COMSOL, and I have a short recording here, so we can look into that one. So here you can see that we have all the relevant controller blocks for the management of the battery, and the functional mockup unit is inside the Simulink, as you can see, surrounded with the relevant blocks. And we have these output scopes to detect and visualize the output temperature, voltage, and the power during the simulation. So let's a little bit fast forward. So here you can see how the voltage is changing during the simulation. As you can see, we wanted to achieve a quite constant power during the simulation. So it's besides the initial state, of course, besides this initial transient part, the output power is quite constant here. And then as the simulation progresses, we can see that the voltage is dropping as we are loading the battery, and also the temperature is rising during our simulation. So we can go a little bit further. Yes, now we are roughly at 500 seconds, and the output power is quite the same. It's probably kept constant. And here from the bottom left corner figure, we can see the temperature is rising. The temperature is still rising, and the voltage, which is on the top right figure, and the voltage across the battery is still decreasing. Okay, a little bit fast forward, a little bit more. Okay, and now it's roughly at 850 seconds, we can see that the power has been turned off. So we stopped the loading of the batteries. And as you can see here, that the temperature rise, which is on the bottom left figure, the temperature rise has been stopped, halted, and of course the voltage drop is also stopped. So you can visualize the effect of this kind of controller that is around our batteries. So you can test your PID controllers, your algorithms, what is happening here around our model, and you can combine both worlds. So you can have a high fidelity model with a finite element modeling of the batteries, the battery packs, so you can have multiples of those, and you can test your control algorithms, what kind of management you can achieve with these settings, with these setups. What will be the maximum temperature? Do you need an active cooling, or maybe the current setup, this passive cooling setup is way enough? So you can test different scenarios for different cases. Okay, and besides this cost simulation, model order reduction, that's also possible. So if you are familiar, or you want to just simply reduce the size of your model, that's also possible. So you can use this reduced order modeling technique, and you can export that into MATLAB or Simulink, and you can run these models using much fewer degrees of freedom. So they will run much faster than the original full fidelity finite element model. So that's also possible using these simulation techniques. So with that said, so this is the demo setup, and you can have the full PDF documentation of that with the full description, with the detailed steps to reproduce the model, and also the model itself, not just the documentation. And that was our brief introduction to this library for Simulink, and how you can add up into COMSOL multiphysics using this functional mockup unit.